Hello everyone, my name is He Guo. I'm a PhD student from Georgia Tech. Today, my topic lies in the intersection of random graph processes and randomness theory. It is based on joint work with my advisor, Ruth Wonke. The main topic of this talk is to introduce a way to construct triangle-free graphs with pseudo-random property in dense graphs. Here are some highlights of our result. Compared to previous results, where previous results only make such construction in complete graphs, well, we can make such construction in dense graphs. And together with the pseudo-random property, it allows us to take out such triangle-free graphs repeatedly. Therefore, we can nearly decompose a complete graph into such triangle-free graphs. And such nearly decomposition solves a conjecture in randomness theory by Fuchs and others. And we can make such construction with high probability by a polynomial time randomized algorithm, not just showing the existence. And because we will run the algorithm for a long time, it's important to control errors. For this purpose, we introduce some self-stabilization mechanism into the process. Before introducing our result, let me briefly review some of the previous results. Erdős in 1961, Spencer in 1977, and Krivolovic in 1994. All of them found an n-vertex graph G in the complete graph Kn, such that the graph G is triangle-free and with impedance number at most some constant C times square root of n times log n. And all of them construct such graph G in the binomial random graph GNP model, where the binomial random graph GNP is a graph that each edge of the complete graph is included independently with probability P. Their result was improved by Kim in 1995 and later on reproved by Bowman in 2008. Both of them found an n-vertex graph G in the complete graph Kn, such that the graph G is still triangle-free but with smaller impedance number compared to the previous result. And as you can see, there is a logarithmic improvement over here. Some combinatorics result tells us that Kim and Bowman's construction is nearly optimal. It means the impedance number is tight up to the constant C. And that was confirmed by Attai, Kamosh, and Smaragdi. This result also leads to the right order of magnitude of the famous randomness number, R3T. And for his breakthrough, Kim also received the Fuchsen Prize in 1997 for this result. And it is known that there are some barriers to apply the binomial random graph GNP to construct a triangle-free graph with a small impedance number. That's why Kim and Bowman need to use some refined way to construct their graph. And both of them use the idea of triangle-free process. Well, the idea of triangle-free process is simple. We start with an empty graph, and at each step, we add one edge that does not create a triangle uniformly at random. And then we repeat. And that is the triangle-free process and was applied by Bowman in his 2008 proof. Well, much earlier, Kim used a semi-random variation of triangle-free process. It means at each step, instead of adding just one random edge, we add many random edges at each step. And that is the difference between Kim and Bowman's proof. Our contribution is that instead of finding just one nearly optimal R3T graph as Kim and Bowman did, we found an almost packing of nearly optimal R3T graphs. It means given any epsilon greater than 0, we find a collection of edge disjoint graphs GI such that each graph GI is nearly optimal R3T graph. That means GI is n-vertex triangle-free and with small independence number. And secondly, the union of the graphs GI in the collection contains at least one minus epsilon fraction of edges of the complete graph. And the idea to prove our packing result is simple. We start with H0 equal to the complete graph Kn, and in Hi, we find the graph GI by semi-random variation of triangle-free process. And then we remove edges of GI from Hi to get Hi plus 1 and repeat. Therefore, we can get our packing result by a simple polynomial time randomized algorithm. And as you can see, the key step here is to find GI in Hi, where the host graph Hi is no longer a complete graph. And that is the point we need our Monte-Koenig result. Our Monte-Koenig result states that if you assume rho is some edge density and S is the size of some large vertex size, then if your host graph H is not too sparse, it means for any two disjoint vertex size A and B of size S, there are epsilon fraction of edges between them in H. It means the number of edges between A and B in H is at least epsilon and size of A and size of B. Then we can find a triangle-free graph G as a subgraph of H, so that the number of edges between A and B in G is roughly the edge density rho times the number of edges between A and B in H for all these joint vertices at A and B of size S. Therefore, as this number is greater than 0, it implies that the independence number of G is at most 2s. It means the triangle-free graph G is a nearly optimal R3T graph. And this formula also tells us that the graph G behaves randomly, and that is a so-called pseudo-random property. And this pseudo-random property guarantees that from the host graph, we remove a similar fraction of edges over all the local parts. And that will imply our packing result. Recall that to get our packing result, we start with H0 equal to the complete graph Kn. And in Hi, we use our Monte-Koenig result to find the GI, where Hi plays the role of H and GI plays the role of G. And then we remove edges of GI from Hi. And the pseudo-random property guarantees that the number of edges between A and B in Hi is roughly this parameter times size of A and size of B. And we can continue removing GI from Hi by this Monte-Koenig result as long as this parameter is at least epsilon. And we will stop when this parameter is roughly epsilon. And then a double counting argument tells us that we have covered at least 1 minus epsilon fraction of edges of the complete graph by the graph's GI. And that is how we use our Monte-Koenig result to prove our packing result. And as discussed, the proof of our Monte-Koenig result is based on semi-random variation of triangle-free process. It does not require degree or codegree regularity of the host graph H. Therefore, the host graph H does not need to be a complete graph. And it is known that controlling errors in one round of the semi-random variation of triangle-free process has already been very hard. But we need to run the process for many rounds. Therefore, controlling errors is important. Otherwise, the error terms will take over. To overcome this difficulty, we introduce some self-stabilization mechanism into the process. And some of the probabilistic tools we use are boundary differences inequalities and some arbitral inequality of Venn. As a summary, instead of finding just one nearly optimal R3T graph as Kim and Bowman did, we found an almost packing of nearly optimal R3T graphs. It means given any epsilon greater than 0, we can cover at least 1 minus epsilon fraction of edges of the complete graph Kn by a collection of edge disjoint graphs Gi, such that each Gi is n-vertex triangle-free on a small impedance number. As remarks, our result is a natural packing extension of Kim's result. And our packing result also establishes some conjecture in Ramsey theory by Fox and others, which I do not have time to discuss here. But if you are interested, I also have a poster with more details about this Ramsey conjecture and more details about our result. That will be presented in these conferences too. Welcome to have a look. Both this talk and the poster is based on a paper by me and Wenke, which has the same title as this talk, and it has recently been published at Combinatorica. Let me stop here. Thank you.